Right. So, hello everyone. It's really great to introduce this session because it's pretty cool, I think. As Volodya described it in the previous session, in this session you will see important breakthrough in conformal prediction. So that's something really to look forward to. And the idea of both kind of talks is to start training conformal prediction by optimizing efficiency directly, which is a very, very interesting venue and a promising direction for loads of joined Royal Holloway as a lecturer. Do you have your mic on? Okay, cool. And yeah, so Nicolo.
Okay, hi. No, sorry, but I think my connection was a bit lost. Thank you for the great introduction. Maybe breakthrough is too big word. Let me try to share the screen. Okay, can you see the right part of my screen?
Perfect.
Okay, so this is the title of my talk, Training Conformal Predictor, as Giovanni said, and this is a collaboration with Volodya. Actually, I should say that I'm pretty new to conformal predictor, so without Volodya, this work would haven't been started. Also, thanks to Volodya to explain patiently all these things to me during this collaboration. And please ask any technical question directly to Volodya just to save time. So this is an outline of my talk. Actually, there are two parts. The first part is very simple. I will try to explain what is the overall idea of this work. And then on the second part, I will explain in slightly more detailed way what we did in the paper. And yeah, I try to keep everything as minimal as possible in these slides. So I remove a lot of details, and probably the notation is slightly wrong, so please do not complain if I try to introduce the basic elements just for you to appreciate the results section. Okay, so but let's start with something that I think everyone knows here, is the standard approach to make conformal prediction. Usually you have a machine learning algorithm or an algorithm in general that is pre-trained, and usually you train by minimize or maximize, or let's say minimizing a loss function, and this loss function is normally an arbitrary loss function that you can choose. You use it to tune the free parameters of your algorithm. And let me stress here that this loss function usually is based on the prediction that for each parameter set your algorithm makes. And these predictions are not conformal prediction, but are normally just pointwise predictions. But this is the first step. So once you have trained your algorithm, then you can, to make conformal prediction, you compute a conformity measure on the top of this algorithm, and then everything is kind of automatic, because given a conformity measure, you can compute p-values, prediction set, predictive distributions, and so on. I think that in all talks there is a nicer introduction to this approach, so I don't repeat it here. And let me just note that this looks like a two-step approach, because the traditional part, that is the first the training of the algorithm. The second part, that is how you make conformal prediction, are kind of autonomous, independent. But usually in machine learning, when you go for a two-step approach, then you should consider some suboptimality issue, because how can you be sure that the best algorithm in the first step is also the best for the second step? It would be way better to treat everything in the same shot, let's say. And this is what actually we do. This is our proposed approach. And the high level idea is to tie together these two parts: the traditional training of the underlying algorithm, and a conformal part where you compute p-values and so on. And how can we tie together these two parts? Our choice is to focus on the optimization. And why we focus on optimization? This comes from a key observation, that for making conformal prediction, first you train your algorithm to make pointwise predictions, and then you use it to make something more refined. So in some sense, you train your algorithm and then you use it to do something else. And this is the gap that we try to solve. So can we train the algorithm in a way that is prepared if the optimal algorithm to do the task that we want the algorithm to do? This is what we do here. Actually, the first problem is that how can we define new objective function, because this is the only thing technically you should do. Volodya presented to me a set of possible objective functions that you can use to measure the efficiency of the conformal predictor that is built on the top of a given algorithm. And these are called criteria of efficiency. And so we define our trained conformal predictor as a conformal predictor that is built in the usual way, but on the top of an algorithm that is that optimize some criteria of efficiency of the whole system. In some sense, we are going from dissonant training, that is the usual approach. I'm sorry, because I know that everyone here is working on this, but this is technically a dissonant training, and what we propose is a consonant training, where the predictive system is trained for the tasks that is supposed to do on the test set. Okay, this was the introduction. Then I go through what we did in practice. That is very, very simple. It's very, very limited. But in the next slide, I will introduce some extra notation just to explain what we did. So as criteria of efficiency, we use observed fuzziness, that is described in this work from 2017 by Volodya, and is actually the sum of the p-values of the wrong classes. And what is nice about observed fuzziness is that you don't need any threshold or fix any conformity parameter, extra parameter. So it's just a parameter-free evaluation of your conformal predictions. Then we focus on the simplest possible machine learning task, that is binary classification of handwritten digits, actually from MNIST. And also we focus on the simplest possible parametric model, that is a one-dimensional model. And why we made this choice is because to avoid any tricky computational part in the optimization, since the model is one parameter model, we can just grid the space and compute the objective function. And this slide is about a bit more technical, what is the object space, the discrete label space, because we have binary classification, so the label space is just 0 or 1, and the object space is the set of images, handwritten images, and we are given a training labeled data set, and we split it. Actually, here, what we are doing is to make split conformal prediction. So we need a pre-train, a pre-test, and d-test. And just to be clear, because pre-train is what is normally called a proper train test, the data set. And the pre-test is what people call calibration data set. And the test is also part, not here, that the test set is also part of the training, because we use it to evaluate the criteria, but during the training step. So just to summarize, what proper train and calibration set are using to evaluate p-values, and then the test is how we evaluate the training criteria by averaging over the result on the d-test, like when you do usual thing with the likelihood, where you average over all the training example in this case. So sorry for this name d-test, but it's actually part of the training set. And here are a few extra things that I should say is, okay, we have a one parameter model, and this model is a conformity measure actually. In the next slide, I will give more details, but let's pick one conformity measure that corresponds to one choice of this parameter theta, and then we can proceed as usual. We compute p-values from the conformity measure, and we can compute observed fuzziness given the p-values. And we can also compute pointwise prediction given the conformity measure as is defined here. So we pick the max of the conformity measure. And as I said before, observed fuzziness is just the sum of the p-values of the wrong classes. And you see here that as we start with the parametric conformity measure, in the end we get some criteria that is also parametric, so it can be treated like exactly like the residual sum of square or a log likelihood of the usual machine learning training, and as a function of this free parameter. And here are the technical, the boring details about the experiment. So as I said, we use the MNIST dataset. I think everyone knows what is the MNIST dataset, but our task is the simplest possible. So we select one of the digits, and we ask the algorithm, the system, to recognize this integer in between all the others. So for example, if we choose the 0, then the label will be 1 for the zeros and 0 for all the other digits in the dataset. We choose, as I said, a one parameter model, and this is the form of the conformity measure. Actually, we are measuring this kernel similarity of the label that are for a given y, let's say, a given label, we check all the objects that have the same label and average their like kernel similarity. This Z is just a way of normalizing. So for example, if we pick a test object that has that is in the middle of all these zeros, and then this kernel similarity will be very high because all the other zeros are pretty close to it. But then I will suggest you to go to the paper for more details and think more about this formula. It's, in general, we are measuring how close one example is to the other example with the same label. And here, this is the general setup of our experiment. So we have two objective functions, and we use, we train two models. One is trained using the conformal objective function, and the other one is trained using the usual objective function, this is PE and F. And then we have two ways of testing. So here, theta star is the optimized value of the optimized model, and we can test it using both this test function, the conformal test function and the pointwise prediction test function. And this is a technical note. To keep validity, we have to further split the training set, but this is just this is a technicality. Please ask Volodya if you have doubt about that. And I will, in the next 3 slides, I will focus on showing some pictures. So here we see the objective. As we have two models and two ways of testing, so in total we have 4 cases, and 2 of them are consonant training, where you train like your algorithm to do a pointwise prediction, and you test with pointwise prediction, or you train in a conformal way and you test on a conformal way. This is the first and the last plot. And the non-consonant cases are in the middle, where you see that there is a gap between the objective function that you use for training, and the objective normally is in blue, and the objective function that you use for testing that is in red. This is a tiny difference, but you see that in the second, I can show here, in the second plot, it looks like the minimum of one of the training objective here is in a different position compared to the minimum of the training of the testing object. So this shows that the result that you get is of course the optimal. The model that you get from the dissonant training is not the optimal one to do the task that you are supposed to do. Here is a comparison of the performance of both the consonant and dissonant training. So on the left, we have both model tested on this prediction error objective, and you see that of course consonant training is always better than dissonant training. So in this case, the model that is trained using the right objective function is getting better and better as the size of the data set increases. So blue here is the prediction error model. And on the other side, we have more or less the same behavior. In this case, we use a conformal, the observed fuzziness criterion to test the models. We see that the model that is trained to optimize the observed fuzziness is actually going better as the the size of the training set increases, and this is you see that the red is the observed fuzziness model, let's say, is going down. And here are some numbers about our experiments. This is for the case where the last case where we have the largest data set that we have tried. We see that I highlighted the best performance in each row, and we see that for both the pointwise and the conformal training and testing, the consonant training is always winning. So I try to highlight only when there is some significant gap between the two performances. And okay, because for dissonant training we had this slightly better performance for conformal training compared to prediction error, but this is a really tiny thing. And so finally, just let me summarize and give you a take-home message. I think that we should not be ambitious here and just saying that consonant training is better. And this is like expected. Everyone knows that if you train something to do a task, and then you should test it on the same task. If you test it on a different task, then you get worse performance. But since it looks like people are interested in making conformal prediction instead of pointwise prediction, so our suggestion is to train conformal predictor instead of using untrained ones if your goal is to make conformal prediction. This is just discussion. It's just a list of limitation of our work. First of all, these are really restricted findings. Simple mode, 1 parameter. Small data set, the MNIST and plus we have selected subset of images, and the task was really easy. The first step forward would be to just use a 10 class, define a 10 class classification model. And then future works include change the efficiency criteria, because observed fuzziness is only one of the possible. But as Volodya said in his talk, we will be probably experimenting with other things. But probably the first improvement to our model is to replace the line search with some gradient descent optimization. This is not easy because, of course, the residual sum of square is a way easier objective to define and to optimize than observed fuzziness, because of all the steps that you need given the model to build this observed fuzziness should be, first of all, approximated in a smooth way, and then we should take the derivative of it. But this is probably the next step we are taking. That's it. Thank you for the attention.